Hi everyone, today we're going to talk about Hess's law and standard enthalpy of formation. Tying to the learning objective, the student is able to draw qualitative and quantitative connections between the reaction enthalpy and the energies involved in the breaking and formation of chemical bonds. Hess's law states that if a chemical equation can be expressed as the sum of a series of steps, then the enthalpy change of the reaction for the overall equation will be the sum of the heat of reaction for each step. Now the rules are that if the reaction is reversed, the sign of the enthalpy change is also reversed from positive into negative or negative into positive. The magnitude of enthalpy change is directly proportional to the mole coefficient. Therefore, if we change the mole coefficient, then we need to multiply the enthalpy change by the same coefficient. Practice problem number 1. Find enthalpy change for the reaction of 4 moles of carbon reacting with 5 moles of hydrogen to form butane. Now we're given 3 equations. The first one, combustion of butane. The second one, combustion of carbon. And the third one, the combination of hydrogen and oxygen to form water. Let's look at that very carefully. We want the butane to form as a product on the target overall equation. Therefore, we need to switch equation 1 and reverse it so that butane would appear as a product. In doing so, the enthalpy change 1 will become positive 2877.8 kilojoule. In terms of the carbon, we want 4 moles of carbon to appear as the reactant. Therefore, we need to multiply equation 2 by the coefficient of 4 and also the delta H2 by 4. In the hydrogen, we want 5 moles of hydrogen to be the reactant. Therefore, we need to take equation 3 and multiply that by 2.5 and also the value of delta H3 by 2.5. So this is a recap of what I just said earlier. Once we have done these changes, now we can add them up to have the overall enthalpy change for the target equation, which then comes up to be 95 kilojoule. The standard enthalpy of formation is the enthalpy change that occurs when 1 mole of a compound is formed from the elements in the standard state under conditions of 1 atm pressure and 25 degrees C. The standard state meaning for gas 1 atm pressure, for liquid or solid pure substances, and for solution 1 molar, and for elements such as oxygen, sodium, mercury, it is 0 because the element is in the most stable form. Now when we write a thermochemical equation, we then write the formation of ethanol from the elements. It comes from 2 moles of carbon and 3 moles of hydrogen diatomic gas molecules and half a mole of oxygen. And the heat of formation, enthalpy of formation is negative 277 kilojoule per mole. So we should really learn how to write these equations, the formation of a compound from the elements, making sure that the atoms are balanced. We also need to apply this equation that the enthalpy change of a reaction is equal to the total enthalpy of formation of product minus the total enthalpy of formation of reactants. Try this problem. When ammonia is burned in air to form nitrogen dioxide and water, and given the following enthalpy of formation data for the compounds, calculate the standard enthalpy change for the overall reaction. 4 moles of ammonia burns with 7 moles of oxygen to form 4 moles of NO2 and 6 moles of water. Now, if we plug the numbers in, it's 4 moles of NO2, 4 times 34 kilojoule per mole, plus 6 moles of water, negative 286 kilojoule per mole, minus 4 moles of ammonia, which is negative 46 kilojoule per mole of ammonia, plus 7 times 0 for that of oxygen, which is element. We got negative 1396 kilojoule for the enthalpy change of the reaction. Now, we can also determine the enthalpy change of formation from the enthalpy change of reaction. given the water enthalpy of formation negative 286 kilojoule per mole, carbon dioxide negative 394 kilojoule per mole, and the enthalpy of combustion of ethene is negative 1411 kilojoule per mole, let's calculate and find the enthalpy of formation of ethene. So now we have a balanced equation first, and we let this enthalpy of combustion, negative 1411 kilojoule per mole, write it on the left-hand side, equal to 2 moles times the enthalpy of formation of CO2 plus 2 moles times the enthalpy of formation of water minus the enthalpy of formation of ethene, which is our unknown variable, plus 0 for that of oxygen. So that's calculated as 51 kilojoule per mole. We can also use bond energy to estimate enthalpy change of a reaction. What's bond energy? It is the energy in a chemical bond, and it is the energy required to break 1 mole of the bond in the gaseous phase. Now let's say if we have 1 mole of hydrogen molecule, we break it down into 2 moles of hydrogen atom, the enthalpy change of the bond energy is 436 kilojoule per mole. Or we have hydrogen fluoride, we want to break it down into the hydrogen atom and fluorine atom, it is 565 kilojoule per mole of bond energy. The compounds with stronger bonds tend to be more chemically stable, meaning less reactive than the compounds with weaker bonds. Bond breaking is endothermic, positive. Bond making is exothermic, energy is released, negative. It will be good for you to remember those 2 last lines. So the enthalpy change of a reaction can be calculated as summation of all the bonds broken minus the summation of all the bonds formed. Because bond breaking is positive endothermic, bond making is exothermic negative, hence you have a negative sign in front of the bonds made. So when the overall enthalpy of the reaction is negative, meaning exothermic, the bond energy of the products are greater than that of the reactants. If the overall enthalpy of the reaction is positive, meaning endothermic, that means the bond energy of the reactants are greater than the bond energy of the products, something we really need to understand. Practice problem number 4, find the enthalpy of combustion of ethanol from the bond energy. So first of all, we need to draw the molecules out of the ethanol and a double bond for the oxygen and a double bond for the carbon dioxide and a single bond for that of the water, and multiply that by the number of moles from the coefficient in the balanced equation. Now we count the number of bonds. I always advise my students to really tabulate it because then we will not easily make a mistake when we substitute the numbers in. So in the ethanol, there are 5 moles of CH bond, 1 mole of C single bond C, 1 mole of CO bond, and 1 mole of OH bond, making sure that you account for all the bonds when you look at the structure of the molecule. Plus 3 moles of double bond O minus 2 times 2, because there are 2 moles of 2 C double bond O in the carbon dioxide, and there are 2 moles, so it's 4 C double bond O, plus 3 times 2, as there are 2 OH bonds per water molecule, so 3 times 2 will be 6 moles of OH bond to be made. So now we plug in the numbers by getting the number from the appendix in your textbook. And we calculate to be negative 1245 kilojoule for 1 mole of ethanol burned. To summarize what we have learned today, we learned how to calculate enthalpy change of a reaction from 3 ways. 1, we did it by Hess's law. 2, we calculated from the standard molar enthalpy of formation. And 3, we calculate from the bond energy of reactant and products. Now you really need to differentiate between 2 and 3. Regarding with number 2 is the enthalpy of formation of product minus that of the reactant. Whereas with the bond energy is the total bond energy in the reactant minus the total bond energy in the product. I hope that you have found this video helpful. If you like it, please give us a like, and I look forward to seeing you in the next video.